Hi everybody, second to last video for the lists file. I wanted to talk to you, just walk through this exercise for you to make sure you get all of the pieces that you need to do and sort of understand what the functions are going to do. So here we want you to define two higher order predicates. That is to say, these are functions that work on lists that, like map and filter, take a function to sort of specify their behavior. So these are functions for characterizing when everything in a list passes a predicate, i.e. the predicate returns true for it, and when there is a thing in the list that passes a predicate. So these are sort of presaging some logical quantifiers we'll talk about a lot in the middle third of the course and the final third of the course. For now, they're just functions. So we want to know, hey, is it true that for everything in the list, some predicate holds? And is it true that there exists something in the list for which the predicate holds? So you could think of these as sort of being related to filter. They're both doing something filter-like. Like you could phrase either of these in terms of a combination of length and filter if you wanted to. We'd like you to define these first as fixed points, and then we'll do a fancier version of Existsb. So we give you a couple of tests just for one of them, hoping that you'll sort of figure out the gist of it. So I want to go through each of these examples for you. Okay, the first one says, if I run the program forallb odd b, so the first parameter of forallb is going to be some kind of predicate. Okay, so we haven't actually told you the type. We're asking for you to infer the type from these examples we've given. So uh, odd b, okay, odd b, if you ran a check, is nat arrow bool. So forallb's first argument here was nat arrow bool. And then it took a list of nats, and then this one should return true. Okay, why? Well, intuitively, we're asking, is everything in the list odd? And the answer is, well, yes, these are the odd numbers between 1 and 10. Cool. So this should return true. Okay, here's another one. forallb neg b. Now, you might not think of neg b as a predicate, right? Neg b is a function that takes bools to bools. But a predicate is a function that returns a bool. So you bet neg b is a predicate. It's a predicate on bools. Kind of a funny way to think about it, but it's a perfectly valid point of view. So is it the case that neg b for everything in this list yields true? And the answer is yes, everything in the list is false. So we should get a true there. Okay, we ask here, forallb even b everything in this list? Is everything in this list even? And the answer is no. There's one thing that isn't. It's right at the end, that 5. 5 is not even. So this should return false because there was just one thing that didn't satisfy it. And then lastly, okay, forallb eqb5. This is the function that returns true when a nat is equal to 5. Does that hold for this empty list? And here our example says the answer should be true. This might be confusing to you. It's like, well, there's nothing in the list. And you're right, there is nothing in the list. But forallb says, is it the case for everything in the list that this predicate holds? Now here, it is vacuously, in the sense of vacuum, empty, or trivially, in the sense of like a tiny, pointless thing. It's trivially true because, right, for everything in the list, for every nothing you can find in the list, it holds. This is in some sense just a convention that a for all of an empty set or an empty list or whatever is going to hold trivially because, like, well, yeah, there's none of them, so of course they're all fine. You know, every unicorn eats brunch every day. There's no way to prove that wrong, right? Because like, there's no unicorns. I'm sorry if that's news. There are no unicorns. It's a tough world out there. So that's the convention for forallb. So Existsb is what's called the dual. It's sort of the mirror image of for all. For all says, hey, is it the case that all of these pass the predicate? Existsb asks, is there at least one? Can you find me just a single thing that passes it? So this first one, Existsb eqb5. Is there anything in the list that's equal to 5? And then the list is 0, 2, 3, 6. No, there's nothing in that list that's equal to 5. Okay, here's another one of these funny Boolean predicates, and be true. Okay, what's that? What does that function do? Well, this it turns out is the identity function on bools, right? It just returns what you give it. And be true true is true, and be true false is false. It just returns its second argument. So okay, does there exist anything in this list for which and be true returns true? Well, and be true returns its second argument, so it'll return true for this one and this one. Existsb just wants there to exist at least one. So the fact that there's more than one, you can't return a truer answer. You just return true. Does there exist an odd number in this list? Yeah, there's two of them, 1 and 3. Solid. Does there exist an even number in this empty list? No. The answer is false. So whereas foralls would sort of vacuously hold, it's like, well, there's nothing here to say anything about, so of course not. Existsb is asking us to find a thing, like it wants a thing in the list that passes the predicate, and there's nothing in this list, so there's no way it can succeed. So Existsb for any empty list is going to return false. Okay, so we want you to write these functions. You're gonna have to figure out the type annotation. We want you to be really comfortable with this. So write it as a fixed point. What are you gonna do? This clearly is some kind of polymorphic function. It's working on nat lists and bool lists. It could probably work on lists of bases and stuff. There's a lot going on. Okay, so how will that work? Lastly, we want you to do one more thing. You actually have three functions to define here. We want you to define a non-recursive version of Existsb. So you can define forallb with a fixed point. You can define Existsb with a fixed point. And we want you to define Existsb prime without a fixed point. You should use it, you should define it in terms of forallb and negb. So play around with it. Try to think about, like, how do you get from a for all statement to an exist statement and back? What do these two things have to do with each other? So your answers should go here. You have to write it all. You have to write, make sure it has the right name, make sure it has the right type. But this is sort of standard for computer programs. Like if your program doesn't have the parts that it needs, then the computer won't run it. So we're trying to get you sort of used to this idea. In the case where you get stuck here, to get the autograder to really work for you, you're probably going to want to write something like this, like saying, like, okay, look, I give up. I don't know how to write this function. Fine, totally cool. Uh, so you're going to want to write definition for all b, and then you need to write the type here. So it'll be for all b colon and then something. If you can't figure that out, take it to Zulip. Let's talk about it. I'm hopeful that everybody will get this problem. It's okay if you don't get all the way on it. Okay. Cool. There's one more short video about our case study that we'll see below. I'm going to talk about DNA strands. That'll be the next video, and then we're done with day 5. All right. Beautiful, folks. Talk to you soon.